Hello. Hello. So today we continue with lecture 3, which is also about oscillatory motion. In today's lecture, we will learn how to compare simple harmonic motion with uniform circular motion. And then we will learn about how the energy is changing in the case of a simple harmonic oscillator. Okay. So just a quick revision for circular motion. Imagine that there is a sphere attached at the end of a string, and I am rotating the string in such a way the sphere undergoes a circular motion with a radius r constant, just as we see over here. Okay, how do we explain the location of the sphere? One way to explain the location of the sphere is by saying, okay, it's making an angle theta, okay, with this axis over here, and it's at a distance r from the center of the sphere. Okay, so this is one way to describe it. When an object goes at an angle theta from an initial position, it also encounters this linear distance, which is called the arc length, S. And if you remember, for circular motion, this S, which is this linear distance, is equal to whatever this radius R is times this angle theta in radian. Okay? The velocity, the linear velocity of the rotating object is equal to R times the derivative, the first derivative of this theta. And we introduce that this theta prime is the angular speed, which we refer to by omega. Now, we have two types of acceleration. One type of acceleration is the tangential acceleration, okay? As it's moving, there is an acceleration in this direction. So if it's here, there is an acceleration in this direction, in this direction, in this direction, okay? Okay, so this is atangential. If it's changing, it means there is atangential. And there is centripetal acceleration, which is in this direction, always toward the center. Okay, so this is called centripetal acceleration. Now, acceleration, tangential acceleration, its formula is r theta double prime, and centripetal acceleration is v squared over r, where v is this v over 2. Now, we are not interested in all types of circular motion. We are only interested in the case when we have uniform circular motion. This happens when A tangential is 0. When A tangential is 0, then v and omega are constants. Okay, when A tangential is 0, then v and omega are constants. Okay, because when A tangential is 0, this means theta double prime is 0. This means theta prime is constant. That's to say v and omega are constants. Okay, so this is one way to describe the location of the sphere. Can we describe it in another way? Another way to describe the location of the sphere, so another way to describe it, so consider a particle P moving with a constant angular speed omega on a circle of radius r. So here we're calling the radius r. Now, the angle theta that represents the angular position P is changing as we are rotating this with a constant omega. This angle theta is equal to omega t plus phi, okay, where phi is the initial position. You can just do the analogy with x equal vt plus x initial. Remember, in horizontal motion, x equal vt plus x initial. Here in circular motion, we have theta equal omega t plus phi, where phi is initial position. Okay, let Q, so now I know that theta is equal omega t plus phi. But if I make the projection of P along the x-axis, okay, and I look now at this triangle, OPQ, okay, if I look at this triangle, OPQ, it's right at Q, right? It's right at Q. So if I take the cosine of angle theta, if I take cosine of angle theta, it's the adjacent side, which is OQ, divided by the opposite side, which is OP. But what is OQ? OQ on the x-axis is x of point Q, right? So it's x divided by OP, which is the radius of the sphere, which here they call it A. Okay, so x is equal A cosine theta. So I have this formula now. X over Q is equal A cosine theta, but theta is omega t plus phi. So xq is A cosine omega t plus phi. This equation now, what does it look like? A cosine x equal A cosine omega t plus phi. This looks exactly like the displacement of a particle in simple harmonic motion. Okay, so here we did a comparison between simple harmonic motion and between the displacement of a particle in simple harmonic motion and uniform circular motion. Now, let's review a little bit of trigonometry. Here. Okay, so x is equal to A cosine omega t plus phi. Cosine and angle is positive when it's positive in quadrant 1 and in quadrant 4, right? If this is here the cosine of angle theta, and this is here the sine of angle theta. Where is the cosine positive? It's positive here and here, right? So the cosine is positive in quadrant 1 and the quadrant 4. It's negative in quadrant 2 and the quadrant 3, right? Here the cosine is negative. What about the sine function? The sine function is positive in quadrant 1 and the quadrant 2, right? So the sine is positive. Let me put it properly for you. So the cosine is positive. Cosine theta positive here. Cosine theta positive here. Cosine theta negative here. Cosine negative here. Okay. In other words, x is positive in quadrant 1. X is positive in quadrant 1 and 4, and x is negative in quadrant 2 and 3. Okay, if x equal A cosine omega t plus phi, how much is V? V is minus A sine omega t plus phi. Okay, when is V? Let's take this is here theta, right? This is here theta. Okay, Now, sine theta is positive in a quadrant 1, implies V is negative. Sine theta positive in a quadrant 2 implies V is negative. Sine theta negative in quadrant 3 implies V is positive. Sine theta negative in a quadrant 4 implies V is positive. Okay, so I get X is positive in a quadrant 1 and 4, negative in a quadrant 2 and 3, V is negative in a quadrant 1 and 2, and positive in a quadrant 3 and 4. Okay, let's do some exercises. So imagine this is a problem. I have an object of mass m and a string of spring constant k. So k equal 5, m equal 0.2. Okay, and the initial position, so here the initial position at t equal to 0, x is equal 5 centimeter, which is 0.05 meter. Okay. Okay, and how much is V at t equal to 0? If it starts from the amplitude, V is 0, right? Starts from rest here, then goes to V maximum, 0, V maximum, 0, etc. Okay, so first part, part A, find the period T. So before we find the period T, we find omega. Omega is the square root of K over M. So this is equal to square root of 5 over 0.2. And this gives 5 radian per second. So this is omega. How is the T related to omega? T is 2 pi over omega, and this gives 1.26 seconds. Okay, so this is part A. Part B. Determine the maximum speed, V maximum equal omega times A. This is equal, omega is 5 times 0.05. This is equal 0.25 meter per second. Okay, part C, A maximum equal omega squared A. This is equal 25 times 0.05, and this is equal 1.25 meter per second squared. Okay, part D, express the position, velocity, and acceleration as a function of time. So let's start with x of t equal a, which is 0.05, cosine omega, which is 5, t plus 5, right? So in order to find phi, so phi is my unknown. To find phi, we use initial conditions. Now, what are my initial conditions? So let's continue here. What are my, at t equal to 0, x is equal 0.05, right? So let's plug this in the equation. So 0.05 is equal 0.05 cosine phi. This implies cosine phi is equal to 1, right? Because 1 times 0.05 is 0.05, implies this gives me one value only for phi, and that is 0. Phi is equal to 0. This means x of t equal 0.05 cosine 5t. V of t is minus V maximum, which is 0.25 sine phi t, and A of t is minus A maximum, which is 1.25 cosine phi t. Okay. Now, if the block was released from the same position, but with V equal minus 0.1. So at time equals 0, X is still equal 5, but V is minus 0.1. So let's change the initial conditions. At E equal to 0, X is still X is still 0.05 meter, but V is minus 0.1 meter per second square. Here I have to pay attention that when it is at 5, the velocity is negative, okay? This means in this case, the amplitude of oscillation was higher than 5 because it was on its way back when it passed by the 0.5. So now this in part E, we have to pay attention that A prime or A is bigger than A. Why? Because the mass, because M was on its way back at time equal to 0. So it was on its way back at time equal to 0. It means it was at a position higher than 5. So the amplitude, the new amplitude is higher than 5. But the M and K are constants, so omega is still the same. Omega is still the same. Omega is still the same because M and K did not change. So omega is still the same value. Omega equal how much? 5. Radian per second. Okay. So if the block was released from the same position, but with V equal minus 0.1, determine the position as a function of time. So here I have to start by saying X of t is equal to this new amplitude cosine phi t plus phi. This phi is also the new phi. Okay, so let's call it phi prime. Okay, so this is X of t, and V of t is equal 5a prime, or we can just call it a. Actually, it doesn't need to be. It's the new a sine 5t plus phi, but it's a new phi as well. Okay, so let's put let's say what is X of 0. X of 0 equal a cosine phi. This is equal to 0.05, implies cosine phi is equal 0.05 over a. Okay, and V of 0 is equal minus, here it's minus 5a sine phi. This is equal minus 0.1, implies sine phi equal minus minus 0.1 over minus 5. So this is 0.1 over 5. Okay. Now, I have the cosine of a function and the sine of a function. We all know that cosine square of any angle, so this is cosine square phi plus sine square phi is equal to 1. So I will continue here, 0.05 over A. So this is 0.05 square over A square plus 0.1 square over 5 square times A square is equal to 1. You can take the A square to the other side. So I get 0.05 square over 1 plus 0.1 square over 5 square. And this gives me A square equal 2.9 e to the minus 3, which implies A is equal 0.0539 e. Okay, e to the minus 3 means times 10 power minus 3. So now in order to find phi, so let's name this angle here. This is, let's take this equation, say this is equation 1. And let's say this is here equation 2, okay? So plug A in equation 1. What do I get? I get cosine phi equals 0.05 over A, which is 0.0539, implies phi is equal plus or minus. Here you have to remember that cosine theta equal cosine minus theta. So this is here equal to 0.05. This is equal to 0.928. Okay, so this is positive. This is positive, implies phi is in quad 1 or 3. Okay, you have to remember back here, if the x is positive, implies it belongs to quadrant 1 or 4. So phi is in quadrant 1 or 3. So phi is equal to plus or minus shift cosine 0.928. Just pay attention that the calculator should be in radian. So I get plus or minus 0.38. Now to know if it is a plus 0.38 or minus 0.38, I have to see, but V is negative, implies, where is V negative? It's in quadrant 1, implies phi is in quadrant 1, implies phi equal 0.38. Okay, so the final equation is, I will put it here, x of t is equal to A, which is 0.0539 cosine omega t plus 0.38. Okay, and this is in Newton. Fine. So again, here you have to remember this drawing over here. This is the most important thing in this section. X is positive. So if X is positive, implies the angle is in quadrant 1 or 4. If V is negative, implies it's in quadrant 1. Okay. If V is positive and X is positive, implies it is in quadrant 4. Now, if X is negative and V is negative, implies quadrant 2. If X is negative, V is positive, implies quadrant 3. Okay, so here you have to remember this circle. Okay. Now, energy of a simple harmonic oscillator. Here we have just to remember formulas of mechanical energy. So when the oscillator is oscillating, okay, there is mechanical energy is conserved. Mechanical energy at A, you just have to remember kinetic energy is half mv squared, okay? Potential energy or EPE is half k x squared. Mechanical energy is kinetic energy plus EPE. Mechanical energy, we refer to it by E. It is equal to kinetic energy plus EPE, which is equal to kinetic energy is half mv squared plus half kx squared. Okay. So these are formulas you need to remember. Now, what is happening at the extremes? At the extremes, the object stops. The object stops, so there is no velocity. There is no velocity. There is only EPE, which means it is half kx squared. But how much is the x at the extremes? It is A. So mechanical energy at the extremes is half Ka squared. Okay, at the extremes, it's half Ka squared. What happens exactly at equilibrium? At equilibrium, x is 0, so there is no EPE, but there is V maximum. So at equilibrium, mechanical energy is half mv maximum squared. At any position x, mechanical energy is half mv squared plus half kx squared. And since the system is isolated, that is, there is no friction, there is no loss of energy, then the mechanical energy is conserved, which means half mv squared plus half kx squared, that is mechanical energy at any time, is equal to the mechanical energy at maximum position or at equilibrium. Okay, if we draw the energies over here, we will see that mechanical energy is constant, it's a straight line. Kinetic energy is 0 at the extremes, then it rises, then it drops. It rises when it reaches until it reaches the equilibrium position, then it drops. Potential energy, it starts from maximum positions at the equilibrium at maximum position, then it drops until it reaches 0. Okay, I will stop here. In next lecture, we will solve problem on the energy.